Chapter 7, Flow. 7.1, Introduction. This chapter discusses the basic terms and formulas used in flow measurements and instrumentation. The measurement of fluid flow is very important in industrial applications. Optimum performance of some equipment and operations require specific flow rates. The cost of many liquids and gases are based on the measured flow through a pipeline, making it necessary to accurately measure and control the rate of flow for accounting purposes. 7.2 Basic terms. Velocity, a measure of speed and direction of an object. When related to fluids, it is rate of flow of fluid particles in a pipe. The speed of particles in a fluid flow varies across the flow, where the fluid is in contact with the constraining walls or the boundary layer. The velocity of the liquid particles is virtually zero. In the center of flow is used in flow calculations. The units of flow are normally feet per second or FPS, feet per minute or FPM, meter per second or MPS, so and so on. Previously, the pressure associated with fluid flow were defined as static, impact, or dynamic. Laminar flow of a liquid occurs when its average velocity is comparatively low and the fluid particles tend to move smoothly in layers as shown in Figure 7.1a. The velocity of the particles across the liquid takes a parabolic shape. The next is turbulent flow. Occurs when the flow velocity is high and the particles no longer flow smoothly in layers, and turbulence or a rolling effect occurs. This is shown in Figure 7.1b. Note also the flattening of the velocity profile. Viscosity is a property of gas or liquid that measured its resistance or motion or flow. A viscous liquid such as syrup has much higher viscosity than water and has a higher viscosity than air. Syrup, because of its high viscosity, flows very slowly and it is very hard to move an object through it. Viscosity or dynamic can be measured in poise or centipoise, whereas kinematic viscosity without force is measured in strokes and or centistrokes. Dynamic or absolute viscosity is used in the Reynolds and flow equations. Table 7.1 gives a list of conversions. Typically, the viscosity of a liquid decreases as temperature increases. The Reynolds number R is a derived relationship combining the density and viscosity of a liquid with its velocity of flow and the cross-sectional dimensions. Ito yung figure 7.1 tsaka yung table 7.1. Flow patterns can be considered to be laminar, turbulent, or a combination of both. Osborne Reynolds observed in 1880 that the flow pattern could be predicted from physical properties of the liquid. If the Reynolds number for the flow in a pipe is equal to or less than 2000, the flow will be laminar. From 2000 to about 5000 is the intermediate region where the flow can be laminar, turbulent, or a mixture of both. Depending upon other factors, beyond 5000, the flow is always turbulent. Bernoulli equation is an equation for flow based on the law of conservation of energy, which states that total energy of a fluid or gas at any one point in a flow is equal to the total energy at all other points in the flow. Energy factors. Most flow equations are based on the law of energy conservation and relate the average fluid or gas velocity, pressure, and the height of fluid above a given reference point. This relationship is given by Bernoulli equation. The equation can be modified to take into account energy losses due to friction and increase in energy as supplied by pumps. Energy losses. Inflowing fluids are caused by friction between the fluid and the containment walls and by fluid impacting an object. In most cases, these losses should be taken into account. Whilst these equations apply to both liquids and gases, they are more complicated in gases because of the fact that gases are compressible. The next is flow rate. Is the volume of fluid passing a given point in a given amount of time and is typically measured in gallons per minute or GPM, cubic per minute or CFM, liter per minute, and so on. Table 7.2 gives the flow rate conversion factors. The next is total flow. Is the volume of liquid flowing over a period of time and is measured in gallons, cubic feet, liters, and so forth. Ito yung table 7.2, the flow rate conversion factors. 7.3, flow formulas. 7.3.1, continuity equation. The continuity equation states that if the overall flow rate in a system is not changing with time, the flow rate in any part of the system is constant, from which we get the following equation. The Q is equals to BA, where Q is equals to flow rate, B is equals to average velocity, A is equals to cross-sectional area of the pipe. The units on both sides of the equation must be compatible. 7.3.2, Bernoulli equation. The Bernoulli equation gives the relation between pressured fluid velocity and the end elevation in a flow system. The equation is accredited to Bernoulli 1738. When applied to figure 7.38, the following is obtained. Ito yung figure 7.3, yung nasa kanan. The units equation 7.6 are consistent and reduced to units of length, feet in the English system and meter the SI system of units as follows. This equation is a conservation of energy equation and assumes no loss of energy between points A and B. The first term represents energy stored due to pressure. The second term represents kinetic energy or energy due to motion. And the third term represents potential energy and energy to height. This energy relationship can be seen if each term is multiplied per unit, which cancels the mass per unit volume is the same at points A and B. The equation can be used between any two positions in a system is in a flow system. The pressures used in the Bernoulli equation must be absolute pressures. In the liquid system shown in figure 7.3b, the flow velocity v at point 3 can be derived from equation 7.6 and is as follows using point 2 as the reference line. Point 3 of the exit dynamic has pressure but no static pressure above 1 atm and hence P3 equals P1 equals 1 atm and G1 equals G3. This shows that the velocity of the liquid flowing out of the system is directly proportional to the square root of the height of the liquid above the reference point. 7.3.3 Flow losses. The Bernoulli equation does not take into account flow losses. These losses are accounted for by pressure losses and fall into two categories. Firstly, those associated with viscosity and the friction between the constriction walls and the flowing fluid. And secondly, those associated with fittings such as valves, elbows, teeth, and so forth. The outlet losses the flow rate Q from the continuity equation for point 3 in figure 7.3b, for instance, gives Q is equals to V3A3. However, to account for losses at the outlet, the equation should be modified to Q equals to C sub D V3A3, where CD is the discharge coefficient that is dependent on the shape and size of the orifice. The discharge coefficient can be found in flow data handbooks. Friction losses. They are losses from liquid flow in a pipe due to friction between the flowing liquid and the restraining walls of the container. These frictional losses are given by H sub L equals FLV squared over 2 dg. The friction factor F depends on the Reynolds number for the flow and the roughness of the pipe walls, where HL equals head loss, F equals friction factor, L is equal to length of pipe, D is equals to diameter of pipe, V is equals to average fluid velocity, G is equals to gravitational constant. Form drag is the impact force exerted on devices protruding into a pipe due to fluid flow. The force depends on the shape of the insert and can be calculated from F is equals to CDY AV squared over 2G, where F is equals to force on the object, CD is equals to drag coefficient, Y is equal to specific weight, G is equals to acceleration due to gravity, A is equals to cross-sectional area of obstruction, V is equals to average fluid velocity. Ito yung table 7.3, the typical head loss coefficient factors for fittings, and the table 7.4 for typical drag coefficient values for object immersed in flowing fluid.
7.4 Flow Measurement Instruments. Flow measurements are normally indirect measurements using differential pressures to measure the flow rate. Flow measurements can be divided into the following groups: flow rate, total flow, and mass flow. The choice of the measuring device will depend on the required accuracy and fluid characteristics, like gas, liquid, suspended particulates, temperature, viscosity, and so on. 7.4.1 Flow rate. Differential pressure measurements can be made for flow rate determination when a fluid flows through a restriction. The restriction produces an increase in pressure which can be directly related to flow rate. So, ang mga examples ng commonly used na restrictions is yung apat. Yung orifice plate, venturi tube, flow nozzle, and dull tube. So, isa-isahin natin sila. Una, si orifice plate. Sabi dito, the orifice plate is normally a simple metal diaphragm with a constricting hole. The diaphragm is normally clamped between pipe flanges to give easy access. So, ayan yung picture ng representation ng orifice plate. Ayan yung orifice plate, color gray yung shaded area. Tapos yung flow is yung fluid na nagpo-flow doon sa ating pipe. Second, okay, Venturi tube. The Venturi tube normally uses a specific reduction in tube size, and it is not used in larger diameter pipes where it becomes heavy and excessively long. So, ito naman, di ba dito, parang naglagay lang ng parang medyo barrier kay orifice plate. Dito naman kay Venturi tube, pinakitid niya tapos pinalapad niya lang ulit. Parang pinasexy niya yung tube, parang ganon. Coca-Cola ang datingan pero nakahiga. So, yung flow, yun yung water or yung fluid or liquid na dadaloy dun sa pipe. Next is the flow nozzle. The flow nozzle is not normally used with suspended particles. Its main use is the measurement of steam flow. O nga pala, hindi nga lang pala liquid or fluid yung dumadali dito sa pipe natin. Pwede yung mga gas. Ito naman yung representation ng flow nozzle. O ganun lang din, pero iba yung naging design. Para siyang may nguso. Kay flow nozzle, kaya nga nozzle. Ito yung nozzle, yung parang nguso. So, yung flow, mga fluid din yon, ganon. Gas, sabi din steam. Mas ginagamit siya sa steam flow, hindi sa mga water, mga ganon. Sa steam siya ginagamit kadalasan. Last but not the least, yung dowel tube. The dowel tube has the lowest insertion but is not suitable for use with slurries. So, dito naman kay dowel tube, as we can see, may magkasalubong na parang barrier na parang kahawig din medyo kahawig ni Venturi tube pero yung kay Venturi tube kasi yun na yung mismong pipe, yung shinape sa ganyan. Pero ito naglagay siya sa loob ng pipe ng barrier or yung restriction. So ito pa yung mga differences nila. Si orifice plate, siya yung pinaka-simple, pinaka-cheap, mas madaling palitan, pero least accurate nga lang siya. And mas madali siyang ma-damage or mag-erosion. And mas malaki yung loss nung pagfo-flow ng ating fluid. Si Venturi tube naman, mas mahirap i-replace kasi mas mahal siya pero accurate siya and mataas yung tolerance niya sa damage and erosion. Tapos yung daloy or yung flow is konti lang yung losses niya. Si flow nozzle naman, intermediate siya between the orifice plate and Venturi tube. So, parang ito yung pinaka-better, si Venturi tube. Tapos, ito yung gitna, si flow nozzle. Tapos, pinakababa si orifice plate. And yung flow nozzle is nag-offer ng good compromise. Si dial tube naman, may advantage naman siya sa pagkakaroon ng mas mababang insertion loss. Kaso, hindi nga siya nagagamit kasi diba dun sa slurries. Ito yung mga iba pang part ng pipe. A, elbow. Ito yun, yung unang picture na sa kaliwa. Elbow can be used as a differential flow meter. When a fluid is flowing, there is a differential pressure between the inside and outside of the elbow due to the change in direction of the fluid. The pressure difference is proportional to the flow rate of the fluid. The elbow meter is good for handling particulates in solution with good wear and erosion resistance characteristics but has low sensitivity. Yung pangalawang drawing naman is si pilot static tube. pilot static tube is an alternative method of measuring the flow rate, but has some disadvantages in measuring flow, in that it really measures the fluid velocity at the nozzle. Because the velocity varies over the cross section of the pipe, the pilot static tube should be moved across the pipe to establish an average velocity, or the tube should be calibrated for one area. Other disadvantages are that the tube can become clogged with particulates, and the differential pressure between the impact and static pressures for low flow rates may not be enough to give the required accuracy. The differential pressures in any of these three devices, this elbow, pilot static tube, and rotameter, can be measured using the pressure measuring sensors discussed in Chapter 5. Yung pangatlong drawing naman, yan yung rotameter. Yung rotameter, isa siyang variable area meter. So, rotameter are often used as a direct visual indicator for flow rate measurement. The rotameter is also a vertical tapered tube with a T or similar lang dun sa T na shape yung weight. As we can see dun sa picture, ayun siya, meron siyang parang patinga. The tube is graduated in flow rate for the characteristics of the gas or liquid flowing up the tube. The velocity of a fluid or gas flowing decreases as it goes higher up the tube due to the increase in the bore of the tube. Hence, the buoyancy and the weight reduces the higher up the tube it goes. An equilibrium point is eventually reached where the force on the weight due to the flowing fluid is equal to that of the weight. The higher the flow rate, the higher the weight goes up the tube. The position of the weight is also dependent on its size and density, the viscosity and density of the fluid, and the bore and taper of the tube. So, yung rotameter is may mababang insertion loss din, katulad ng dial tube, and merong pagka-linear relationship dun sa flow rate. In cases where the weight is not visible, an opaque tube used to reduce corrosion and the like. It can be made of a magnetic material and tracked by a magnetic sensor on the outside of the tube. The rotameter can be used to measure differential pressures across a constriction or flow in both liquids and gases. Isang example ng rotating flow rate device is yung turbine flow meter. The turbine rotor is mounted in the center of the pipe and rotates at a speed proportional to the rate of flow of the fluid or gas passing over the blades. Wherein yung turbine blades na sinasabi natin is normally made of magnetic material or ferrite particles in plastic so that they are unaffected by corrosive liquids. So, ito yung picture ulit ng turbine flow meter. Ayun yung flow, yung liquid or gas. O yung rotor, ito yung umiikot. Alam naman na natin yon. Tapos magnetic sensor para yung rotor is iikot siya or madetect yung natunga ng sensor yung pag-ikot ng rotor. As the blades rotate, they can be sensed by a Hall device or magneto-resistive element, MRE. Sensor attached to the pipe. Ito nga yung magnetic sensor, MRE. The turbine should be only used with clean fluids such as gasoline. The rotating flow devices are accurate with good flow, operating, and temperature ranges, but are more expensive than most of the other devices. Another one is etong moving vane. Yung moving vane is a device that can be used in a pipe configuration as shown or used to measure open channel flow. The vane can be spring-loaded and able to pivot. By measuring the angle of tilt, the flow rate can be determined. Tapos meron naman tayong iba't ibang klaseng meters. So first one is the electromagnetic flow meters. It can only be used in conductive liquids. The device consists of two electrodes mounted in the liquid on opposite sides of the pipe. A magnetic field is generated across the pipe perpendicular to the electrodes. The conducting fluid flowing through the magnetic field generates a voltage between the electrodes, which can be measured to give the rate of the flow. The meter gives an accurate linear output voltage with flow rate. Wala siyang insertion loss and yung reading niya are independent doon sa mga characteristics ng fluid. Pero it is a relatively expensive instrument. So, second one na yung vortex flow meters. This is based on the principle that an obstruction in a fluid or gas flow will cause turbulence or vortices, or in the case of the vortex precession meter para dun sa mga gas, the obstruction is shaped to give a rotating or swirling motion, forming vortices, and this can be measured ultrasonically. The frequency of the vortex formation is proportional to the rate of flow, and this method is good for high flow rates. At low flow rates, the vortex frequency tends to be unstable. Mas mainam gamitin yung vortex flow meters kapag high yung flow rates natin. Pero kapag low lang yung flow rates natin or mababa lang yung value niya, hindi magandang gamitin yung vortex frequency kasi mabagal na yung flow or mababa. So, kapag gumawa tayo ng swirling motion doon, hindi siya masyadong magsa-swirl or hindi siya masyadong ikot. So, parang hindi rin natin mami-measure ng mabuti or hindi mami-measure ng mabuti ng vortex flow meter yung flow rates. Yung third one natin is yung pressure flow meters. Pressure flow meters use a strain gauge to measure the force on an object placed in a fluid or gas flow. The force on the object is proportional to the rate of flow. The meter is low cost and medium accuracy. So, pinaka-better talaga yung electromagnetic flow meters, kaso nga lang mahal siya. Pero kung magtitipid ka, pwede ka na din sa pressure flow meters, kaso nga lang, di siya masyadong accurate. Parang sakto lang. Moving on sa 7.4.2 total flow. Includes devices used to measure the total quantity of fluid flowing or the volume of liquid in a flow. Positive displacement meters use containers of known size which are filled and emptied for a known number of times in a given time period to give the total flow volume. Two of the more common instruments for measuring total flow are the piston flow meter and the nutating disc flow meter. So, yung piston meters consist of a piston, syempre piston, in a cylinder. Alam naman na natin ata yun. Parang, parang matik nang alam na natin yan kasi nag-aralan natin last sem yan or last sem, something ganon. Initially, the fluid enters on one side of the piston, filling the cylinder, at which point the fluid is diverted to the other side of the piston via valves and the outlet port of the full cylinder is opened. The redirection of fluid reverses the direction of the piston and fills the cylinder on the other side of the piston. The number of times the piston traverses the cylinder in a given time frame gives the total flow. The meter has high accuracy but is expensive. Sa notating this naman, nu- notating these meters are in the form of a disk, disk nga eh, notating this, so this siya, that oscillates, allowing a known volume of fluid to pass with each oscillation. The meter is illustrated in figure 7.9a. Mamaya, pakita natin yan. The oscillations can be counted to determine the total volume. This meter can be used to measure slurries but is expensive. Yung velocity meters naman is normally used to measure flow rate. Can also be set up to measure the total flow by tracking the velocity and knowing the cross-sectional area of the meter to totalize the flow. So, bale meron tayong tatlong meters pagdating sa total flow. Yung dalawa, expensive, simulating this, saka yung piston meters. Sa velocity meters, kadalasan naman kasi ginagamit siya sa flow rate, pero pwede rin sa total flow. Kapag nga daw, alam natin yung cross-sectional area nung ating meter. Mag-move on na tayo sa 7.4.3, mass flow naman. So, mass flow. By measuring the flow and knowing the density of a fluid, the mass of the flow can be measured. O, dali, di ba? Kapag may density kang given ng fluid, madali nang alamin yung mass na yon. Mamaya papakita natin yung formula para doon. Mass flow instruments include constant speed impeller turbine wheel spring combinations that relate the spring force to mass flow and devices that relate heat transfer to mass flow. Anemometer. Anemometer is an instrument that can be used to measure gas flow rates. One method is to keep the temperature of a heating element in a gas flow constant and measure the power required. The higher the flow rate, the higher the amount of heat required. The alternative method is to measure the incident gas temperature and yung temperature ng gas downstream from a heating element. Yung difference ng two temperatures na yon is can be related to the flow rate. Micro-machined anemometers are now widely used in automobiles for the measurement of air intake mass. The advantages of this type of sensor are that they are very small, have no moving parts, pose little obstruction to flow, have a low thermal time constant, and are very cost effective along with good longevity. Moving on dun sa may formula, sa 7.4.4, dry particulate flow rate. So, ano ba yung dry particulate flow rate? Dry particulate flow rate can be measured as the particulate are being carried on a conveyor belt with the use of a load cell. This method is illustrated in figure 7.9b, yung kaninang picture. Yung pangalawa, ayan. Ay yung belt, yung line na yarn. Tapos, ito yung parang wheel or bearing or gear para mag-move yung belt. Tapos, ayun yung fluid tumatapon. So, to measure flow rate, it is only necessary to measure the weight of material on a fixed length of the conveyor belt. So, ito yung formula nga na sinasabi ko kanina. The flow rate of Q is given by Q equals WR over L. Wherein yung W natin dyan is si weight of material on length of the weighing platform. Yung L natin is length of the weighing platform. Yung R naman is yung speed of the conveyor belt. Next na tayo ulit. 7.4.5, open channel flow. Open channel flow occurs when the fluid flowing is not contained as in a pipe but is in an open channel. Flow rates can be measured using constrictions as in contained flows. So, etong sa kaliwang picture, this device is similar in operation to an orifice plate. Parehas daw sila ng operation ni orifice plate. The flow rate is determined by measuring the differential pressures or liquid levels on either side of the constriction. Yung nasa kanan naman, etong nasa baba, sa lower right, ang tawag sa kanya is partial flume. A partial flume which is similar in shape to a Venturi tube. Ito namang si partial flume, katulad naman daw siya ni Venturi tube. A paddle wheel or open flow nozzle are alternative methods of measuring open channel flow rates. Kung titingnan nga natin yung drawing, di ba parang katulad nga talaga siya ni Venturi tube. Etong si partial flume. Ito namang si Weir, na Vinach Weir. Kamukha siya ni Orifice kasi para siyang isang plate lang. Parang plate nga lang siya na barrier or constriction na meron lang konting space na dadaluyan ng ating fluid. Let's move on to 7.5. Application considerations. Many different types of sensors can be used for flow measurements. The choice of any particular device for a specific application depends on a number of factors such as reliability, cost, accuracy, pressure range, temperature, wear and erosion, energy loss, ease of replacement, particulates, viscosity, and so forth. 7.5.1 Selection. The selection of a flow meter for a specific application to a large extent will depend on the required accuracy and the presence of particulates, although the required accuracy is sometimes downgraded because of cost. One of the most accurate meters is the magnetic flow meter, which can be accurate to 1% of full scale reading or deflection or FSD. The meter is good for low flow rates with high viscosities and has low energy loss, but is expensive and requires a conductive fluid. The turbine gives high accuracy and can be used when there is vapor present, but the turbine is better with clean, low viscosity fluids. Ito yung table na nagbibigay ng comparison ng mga flow meter characteristics. The general purpose and most commonly used devices are the pressure differential sensors used used with pipe constrictions. These devices will give accuracies in the 3% range when used with solid state pressure sensors which convert the readings directly into electrical units or the rotameter for direct visual reading. The Venturi tube has the highest accuracy and least energy loss, followed by the flow nozzle and the orifice plate. For cost effectiveness, the devices are in the reverse order. If large amounts of particulates are present, the Venturi tube is preferred. The differential pressure devices operate best between 30 and 100% of the flow range. The elbow should also be considered in these applications. Gas flow can be best measured with an anemometer. Solid state anemometers are now available with good accuracy, are very small in size, and are cost effective. For open channel applications, the flume is the most accurate and best if particulates are present. but is the most expensive. Particular attention should also be given to manufacturers' specifications and application notes. 7.5.2 Installation naman. The position of the pressure taps can be critical for accurate measurements. The manufacturer's recommendations should be followed during installation. In differential pressure sensing devices, the upstream tap should be 1 to 3 pipe diameters from the plate or constriction, and the downstream tap up to 8 pipe diameters from the constriction. To minimize the pressure fluctuations at the sensor, it is desirable to have a straight run of 10 to 15 pipe diameters on either side of the sensing device. It may also be necessary to incorporate laminar flow planes into the pipe to minimize the flow disturbances and dampening devices to reduce flow fluctuations to an absolute minimum. Flow nozzles may require a vertical installation if gases or particulates are present. To allow gases to pass through the nozzle, it should be facing upwards, and for particulates, downwards. Ito, 7.5.3 yan. Calibration. Flow meters need periodic calibration. This can be done by using another calibrated meter as a reference or by using a known flow rate. Accuracy can vary over the range of the instrument and with temperature and specific weight changes in the fluid, which may all have to be taken into account. Thus, the meter should be calibrated over temperature as well as range, so that the appropriate corrections can be made to the readings. The spot check of the reading should be made periodically to check for instrument drift that may be caused by the instrument going out of calibration, particulate buildup, or erosion. So, summary na tayo. Yung chapter na to, diniscuss natin yung measurement of the flow of fluids in closed and open channels and gases in closed channels, yung basic terms, standards, formulas, and laws na associated dun sa flow ng rates, yung instruments used sa pagme-measure ng flow rates, and yung description na to, as well as yung consideration sa pag-apply ng mga instruments. The salient points discussed in this chapter are as follows. Number one, a relation of the Reynolds number to physical parameters and its use for determining laminar or turbulent flow in fluids. Two, the development of the Bernoulli equation from the concept of the conservation of energy and modification of the equation to allow for losses in liquid flow. Three, definitions of the terms and standards used in the measurement of the flow of fluids and slurries. Four, difference between flow rates, total flow, and mass flow, and the instruments used to measure total flow and mass flow in liquids and gases. 5. Various types of flow measuring instruments, including the use of restrictions and flow meters for direct and indirect flow measurements. 6. Open channel flow and devices used to measure open channel flow rates. 7. Comparison of sensor characteristics and considerations in the selection of flow instruments for liquid and slurries and installation precautions. Thank you.